This is a video on power and errors. In this video I'm going to work through 3 examples from chapter 21 of your book. So if you want to follow along in your book, that's fine. I've also typed the examples into here. It's chapter 21, problems 27, 29, and 33. So number 27, a statistics professor has observed that for several years about 13% of the students who initially enroll in his introductory statistics course withdrew before the end of the first semester. A salesman suggests that he tries a statistics software package that gets students more involved with computers, predicting that it will cut the dropout rate. The software is expensive, and the salesman offers to let the professor use it for a semester to see if the dropout rate goes down significantly. The professor will have to pay for the software only if he chooses to continue using it. Part A. Is this a one-tailed or two-tailed test? And explain. Well, since he's only interested in cutting the dropout rate, then he only wants to know if it's going to lower the dropout rate. So this is a one-tailed test. The claim of the salesman is that it's going to cut the dropout rate. That's the claim that he's testing. So it's a one-tailed test. Since he's only interested in cutting the dropout rate. He's certainly not interested in raising the dropout rate. Okay, write the null and alternative hypotheses. The null hypothesis, H0, is that his dropout rate, that proportion, is 0.13, where P is the proportion of students who drop out of the class with software being used in the class. He wants to know whether the software is going to be effective or not. So his null hypothesis is that it's not going to change things, that the dropout rate is still going to be 13%. The alternative hypothesis is that it's going to help. It's going to lower that proportion to be less than 0.13. Okay, in this context, explain what would happen if the professor makes a type 1 error. Type 1 error means rejecting the null hypothesis when he should not be rejecting it. Should not be rejecting it means it's true, it's not changing. So a type 1 error here is that he buys the software. That would be rejecting the null hypothesis when it's not going to reduce the dropout rate. So rejecting the null hypothesis means he's going to buy the software. But a type 1 error is that he rejects the null hypothesis when he shouldn't. So he shouldn't reject the null hypothesis if that software is not going to help anything. Alright, in this context, explain what would happen if the professor makes a type 2 error. Type 2 error is failing to reject the null hypothesis when you should reject the null hypothesis. So failing to reject the null hypothesis means he thinks the null hypothesis is correct, so that means he's not going to buy the software. Because he thinks it's not going to work. However, type 2 error is failing to reject it when he should reject it because really the software did work. So type 2 error here would be not buying the software when he should buy it, since it will reduce the dropout rate. Alright? What is meant by the power of this test? So power is the likelihood of your test to reject the null hypothesis when it should reject the null hypothesis. So in this case, it's the probability or the likelihood of correctly deciding that the software will lower the dropout rate. If the software will lower the dropout rate, then we should be rejecting the null hypothesis. So the power of the test is its ability to detect or correctly decide that we should buy the software because we know that it lowers the dropout rate. Number 29. Initially, 203 students signed up for the stats course listed above. They used the software suggested by the salesman, and only 11 of those 203 students dropped out of the course. So should the professor spend the money for this software? Support your recommendation with an appropriate test. Well, what is that proportion from this particular sample? What's the p-hat? Well, it's 11 out of 203, which is 0.054, 5.4%. That's less than 13% by a good margin. Is it far enough below 13% to give us convincing evidence that this is going to happen, that this is going to pay off every semester, and it's not just that our random sample gives us these results by chance? So the appropriate z-test would be a one-prop z-test. We'll perform one with the significance level of 0.05 and alpha of 0.05. Remember, we need to state that up front. Our null hypothesis is what we said above, that p is equal to 0.13. Our alternative hypothesis is that p is less than 0.13. Before we proceed, we must check the conditions. So we need randomness. Now, you'll notice our sample here is everybody who's in this course for this particular semester. That is a sample because it's a sample of all of his statistics students that he'll have from here on in the rest of his career. So he's using this semester as his sample of the population of all of his statistics students because he wants to know if this is going to be worth buying to use every semester. So we can assume that this semester is representative of all of his typical semesters of students, and therefore that randomness is satisfied. So this semester should be representative of other semesters. So randomness is satisfied. The whole point of randomness is to give us a sample that's representative of the population. All right. Next condition, we assume each semester of students is independent of the other semesters of students. That this sample has independence with the rest of the population. And then the third condition, n times p is 203 times 0.13. Remember, we used the p from the null hypothesis. That's certainly greater than 10. And n times q is 203 times 0.87, which is also certainly greater than 10. So we satisfy that condition, the 10 successes and 10 failures, which tells us we have an approximately normal distribution, and therefore we can use a one-prop z-test, because z requires the normal distribution. All right, now we can proceed. We find our z statistic. We could do this on the calculator, or we can do it by hand. The formula for doing it by hand is p hat minus p naught over the square root of p naught q naught over n. So that would be 0.054 minus 0.13 over the square root of 0.13 times 0.87 over 203, which works out to be negative 3.22. Is it okay to get a negative? Absolutely. That means it's 3.22 standard deviations lower than p naught. That's good. We want to be low if we want to be lower than 13%. So we've got our z value. We use that to find the p value. P value is the probability that z is less than or equal to negative 3.22, assuming that the null hypothesis is true. So we use the normal CDF. negative 1,000 up to negative 3.22, standard deviation of 1 and mean of 0, gives us a probability of 0.00064. Again, you could do the one prop z-test on your calculator, and you will get numbers very close to the z and the p that we got here. So, we make our conclusion. P, which is 0.00064, certainly less than our alpha, which is 0.05. P is less than alpha. The immediate conclusion is reject H naught. The implication is there is convincing evidence. Anytime we reject H naught, we say there is convincing evidence for the alternative hypothesis. So there is convincing evidence that the true dropout rate when the software is used is less than 0.13. So that means for this problem, yes, he should consider buying the software. Because we seem to have evidence that buying the software is going to lower the dropout rate. How far is it going to lower it? We don't know. But it's likely to be less than 0.13. That's all our test tells us. Part B. Explain what your p-value means in this context. Well, remember the p-value is 0.00064. P-value is the probability of getting a value at least as extreme as the one we got in our sample if the null hypothesis is true. So that means there is a 0.064% chance of obtaining the statistic of 5.4% or fewer dropouts, so at least as extreme as the value we got, 5.4% or less dropouts by random chance if the null hypothesis were true, so if the actual dropout rate with software is actually still 13%. So the p-value is the likelihood of this happening by random chance if the null hypothesis were true. Very low probability that it happened by random chance, therefore we assume the null hypothesis is not true. That's our conclusion. Okay. Problem number 33. A basketball player with a poor foul shot record practices intensively during the off-season. He tells the coach that he has raised his proficiency from 60% to 80%, so he claims he's gotten better at making foul shots. Dubious, he doesn't believe him, the coach asks him to take 10 shots, and is surprised when the player hits 9 out of 10. Pretty good. Did the player prove that he has improved? Your immediate thought should be, no, he's proved nothing. But, part A, suppose the player really is no better than before. Suppose he's still actually a 60% shooter. What's the probability that he can hit at least 9 out of 10 anyway? Because it could be that the sample's too small, he just happens to make 9 out of 10, even though he's really only going to make 60% of his shots. Well, if you think about it, this probability is a binomial situation. Either he makes a shot or he doesn't. So we want any combination of making at least 9 out of 10 shots. So maybe he misses the first one and then makes 9, or makes the first one, misses the second one, and then makes 8 more. So we have to do it as a binomial situation. And at least 9 is 1 minus the probability of 8 or less. So 1 minus binom CDF of 10.6 and 8, where this is certainly binomial. With an n of 10, p of 0.6, and a number of successes of 8. So 1 minus that gives us at least 9 or 10, and that is 0.0464. So about 5% chance that he can make 9 out of 10 if he has not changed his success rate from 60%. If that is what happened, now the coach thinks the player has improved when in fact he hasn't. Which type of error is made? Well, he has rejected the null. The coach has rejected the null hypothesis. The null hypothesis being that his proportion is still 0.6 when he shouldn't have rejected it. So which error is it when you reject the null hypothesis when you shouldn't? That's a type 1 error. Okay, so that's one scenario, is that his success rate has not changed from 60%. The other scenario is it actually has changed. So part C, if the player really can hit 80% now, and it takes at least 9 out of 10 successful shots to convince the coach, what's the power of this test? So remember, power is the probability of rejecting H0 when you should. So in this scenario, that's the probability of getting at least 9 out of 10, because that's what's going to make the coach reject the null hypothesis, at his 80% success rate, because in this scenario he really has changed. So he should be rejecting it if his success rate is 80%, but he's only going to reject it if he gets 9 out of 10. At least 9 out of 10. So how do we find the probability of making at least 9 out of 10 shots at an 80% success rate? Again, it's a binomial situation where it's going to be 1 minus binom CDF of making 8 or less, but this time at an 80% success rate instead of a 60. So 10.8 and 8. That probability is 0.3758. So about a 38% chance that he will make 9 out of 10 shots if he can do so at an 80% success rate. So let's list 2 ways the coach and the player could increase the power to detect the improvement. Well, remember we had 4 ways that we could increase the power. Really, there's only 2 of them that we have control over. We can't control the effect size, but we can control the sample size. Sample size here is the number of shots he takes. So we could go for a bigger sample size. Bigger sample size means more power, or bigger sample size here means take more than 10 shots. Right? Another way we can increase power is to keep it at 10 shots, but don't only be satisfied by 9 out of 10. Maybe you'll be satisfied by 8 out of 10. So keep it at 10 shots, but decide that at least 8 is good enough. What is that really doing? That's really increasing alpha, increasing your significance level. You're saying, I don't need such a small probability in order to be convinced. I'll be convinced by a slightly larger probability of it happening. Any questions? No? Good. That's it.